Hello, everyone. Today, I'll be talking about using magnetic skyrmions with chambers for new generation computing. I will not bore you with too much for details. I will try to tell a story today. If you're interested, if you have access to our papers, you can read more on the details. But I've divided it into two main sections. I will do a quick review. I know that we had talks on skyrmions and on the VCMA, voltage controlled magnetic anisotropy. So I will do a quick review, and then I will move to the main topics. So I want to go over some of the backgrounds, properties, techniques we have, and then I will sum them together into a beautiful story. So this is a good quote I found from a Nature paper that describes well what are the potentials of magnetic skyrmions. And if you're interested, it's actually from a simulation. This is how it looks like. In a sense, it's basically a defect that was found decades ago. First, it was discussed. It was discussed in high energy physics. Like theoretically, it has been found. But then, of course, everything comes to engineering whenever someone finds a way to experimentally verify it. So magnetic skyrmions have been in trend in the last decade. So what are the magnetic skyrmions? They're basically bubbles, but they're like its official name is a quasi-particle. It's a swirling quasi-particle. They're not of twisting field lines that can be manipulated. You can move them around, and they're topologically stable, which means you can't really destroy them easily if given the right conditions to create them. We have two types, but this is similar to the class, like in domain walls, Bloch and Neal, if you remember from our class. One of them is the spin rotates in plane, and the other one is out of plane. But yeah, if you are interested in the picture, the black is pointing down, white is pointing up. So it is like a defect that someone observed, and they said, why not to do computation using magnetic skyrmions? Now, why I'm focusing on chambers? Because we know that magnetic skyrmions are important because they're energy efficient. We know that they can be manipulated using low current, but they have some problems. For example, like in the beginning, people found a way to move them using currents, the techniques that we've discussed in class, SOTs, STTs. Then they were able to detect and create them. So that was the second major milestone. And then people got creative. For example, they tried to come up with different designs. You can think of this as a circuits, but this is like magnetic circuits. And the skyrmions that you see here, they are represented as bits. But there is a problem because controlling skyrmions is a little bit hard. Keeping them stable is a little bit hard. One of the main issue is its skyrmion's Hall angle. Like it always moves in the plus and minus z direction when you move it in x and y direction. So, when you move it in x or y, you will always get this effect of Hall angle in the z direction. So now, in order to solve that kind of problem of keeping the skyrmion stable, they said why not to bring chambers, because inside the chamber you can create a bunch of them. For example, they can crash to the walls, or for example, they can get unstable, but you will still have majority of those skyrmions inside the chamber. So you can use it for computation. So like the whole discussion started back in 2018 with the proposal on the right. Then experimentally, it was verified in 2019. That's when the interest came to engineering, I guess. But you can still see the same problems. For example, when they tried to experimentally observe the motions. This is in second nanoscales. So for example, if you would use it in an actual circuit, you would need something much more faster. That's when this Hall angle would prevail again. But in the beginning, let's look at the concept. So the concept was that you would introduce the skyrmions. They would have skyrmions would interact with each other if you remember from the previous talks, skyrmions can interact with each other, they can interact with the walls, and they have their whole angle. These three parameters can make them move in random directions. So that's why the proposal that came in 2018, it was proposed for probabilistic computing, because you can create probabilistic bit streams. Now, another direction that the field is moving is on reservoir computing. One of them is probabilistic computing, because it has skyrmions properties are random, that creates random bit streams. Or another direction is you can do reservoir computing. But for this, the interplay between the weights inside your chamber comes into play here. But not much has been done further than that 2019 experimental paper I've shown you, because I mean, they found out that it's not that easy to gather all of these inside a circular chamber. So now the field is moving more towards using VCMA for the chambers, because when we know that with you can manipulate skyrmions using voltages. When you apply voltage in Z direction, you can create electric field that affects the magnetic properties of your material. In that way, you can precisely control the movements. There has been some papers that try to show that you can come up with different schematics to do computation, but this VCMA didn't fully come into more chamber-based approach of the skyrmions yet. So it's in the research stage. For example, that's what makes it interesting, because VCMA plus the skyrmion reshufflers, it can actually bring this ultra low power consumption, because VCMA in recent papers have been shown that it's very low. It uses way less energy than SOT and SCT techniques we use. And it's more stable, and you can use high density processing, because since you can precisely control, you can control the distances between skyrmions. Now, what is the idea, if you're wondering? So the whole idea is, at least that's my perception from the papers, is basically using these four fundamental properties that VCMA brings for skyrmions. And it's like solving a puzzle. You take these four pieces, try to put them together, and try to come up with new computational schemes. One of them is VCMA creates higher or lower anisotropy. By using that, you can repel skyrmions, you can block the movements of the skyrmions, you can decrease or increase their diameters, or you can limit the movements. So you can take these pieces of the puzzle and you can try to come up with your own computational scheme. Apart from that, let me show you something else. Definition of a chamber is a bit ambiguous. For example, can we consider this a chamber or not? This is up to you. But this is one of the papers, for example. It has been shown that you can use those chambers to try to mimic the synapse in human brain. You can mimic the neurons synapse. That means you can actually do neuromorphic computation too. So using those fundamental properties of the brain, you can try to do neuromorphic computing with these chambers. Now let's go to the problems. Growing these are not easy, as in domain walls. For example, a lot of study is focusing now on how to create them more efficiently or how to make it more stable. But in the growth process, it has its own phases. That's something I wanted to show, but my computer died. Yeah. Okay. What makes it difficult is because you get those bubbles out of these strip-line domains. You have to tune either your thickness, or you can influence it from outside. For example, you can apply electric current to change its DMI, or you can apply electric field, or you can change the temperature gradient, or you can apply voltage by changing the anisotropy, so that you would get the right condition to get those bubbles. That's what makes it hard. Now, this is the example for the multi-layer. when you stack more layers, they make it more stable. That's where the direction of the research is going these days. But it still has its challenges. We don't know what material selection is one of its major challenge. Fabrication, we don't really fully know how to read, write, or how to connect it with the CMOS or any other circuit we have now, how to control it, how to overcome these challenges is an active research. But it has, but in my opinion, this introducing chambers to skyrmions has a good outlook, because otherwise the other schematics that I've shown, those would be much harder to show experimentally. I mean, you might analytically or in simulation show that it's possible, but in experiments it would be hard to get them otherwise. And then these are the references I wanted to show.